Some technology exists because it solves a hard problem. Other technology exists because somebody shipped a compromise, everybody copied it, and eventually the compromise became infrastructure. Today, 5 technologies enter the courtroom: the phone notch, Microsoft's ribbon, the fax, consumer DRM, and blockchain, where a normal database would do. None of them is completely useless. That would be too easy. These are more interesting. Ideas with a rational origin that escaped containment. To be fair, should never have existed is deliberately dramatic. Engineers rarely choose between perfect and terrible. They choose between deadlines, costs, physics, compatibility, and whichever executive has the strongest opinion. So our test is not whether a technology ever worked. It is whether its benefit justified the complexity it exported to everyone else. Did it remove a problem or merely relocate it? And once the world depended on it, did we keep it because it was good or because deleting it became too expensive? With that settled, exhibit number 1 is probably cutting into your screen right now. In 2017, the iPhone X pushed the display towards every edge while keeping a front camera and a cluster of sensors for Face ID. Those components needed somewhere to live. Apple kept an island of hardware at the top and wrapped the screen around it.
The engineering trade was defensible. The strange part was what happened next. A physical obstruction became a software problem for everybody. Interfaces had traditionally treated a display as a rectangle. Now the rectangle had unsafe regions. Operating systems introduced safe area guides. Web layouts gained environment variables, such as safe area inset top. Games, video players, navigation bars, adverts, and full screen buttons all had to decide whether to avoid the cutout, embrace it, or accidentally hide something underneath it. That does not mean every developer wrote thousands of lines of notch code. Platforms abstracted much of the work. But abstraction does not erase complexity. It standardizes it. Every layout engine now carries rules for shapes that are almost rectangles. And the alternatives were not free. Pop-up cameras added motors and failure points. Thick bezels looked dated. Early under-display cameras compromised image quality. The notch won because it balanced those costs, and because it was immediately recognizable. Then the compromise became fashion. Notches became teardrops, punch holes, and floating islands. We gained more screen area, but also a permanent negotiation between physical sensors and virtual content. Verdict? Not useless. Just technical debt with excellent branding.
Next, Microsoft Office 2007 and the ribbon, a wide strip of tabs, groups, icons, galleries, and contextual controls that replaced the old stack of menus and toolbars. Microsoft had a real problem. Office had accumulated so many features that users routinely asked for tools which already existed. Commands were buried 3 menus deep. The ribbon made them visible, grouped them by task, and gave common actions larger targets. For a new user, that can be genuinely better. For an experienced user, it was as if somebody reorganized the kitchen overnight, labeled every drawer, and then congratulated you because the spoons were now more discoverable. Muscle memory is part of an interface. A command is not merely present. It has a location, a path, and a rhythm. Replace file, edit, and format with home, insert, and layout, and the feature still exists, but the user's internal map does not. The ribbon also spends vertical space to advertise capability. That makes sense for discovery, but less sense once the user already knows the 10 commands they use every day. Office 2007 initially offered limited customization, so power users paid the migration cost without having much control over the new map. Later versions added better customization and collapsing, but by then the ribbon had spread across Microsoft software and beyond.
That does not prove the ribbon failed. It solved enough of the discoverability problem to survive, but it fixed feature overload by building a louder, more elaborate map of the overload. Verdict: a successful interface and a monument to software bloat. Next, fax. Its earliest concepts predate the telephone. Alexander Bain patented an electric printing telegraph in 1843. A traditional fax scans a page, encodes it as image data, sends that data through a voice-oriented telephone connection, and reconstructs the image at the other end. text becomes pixels. Searchable fields become a flat picture. A digital document can be printed, scanned, transmitted, received, and typed back into another computer. That is not a data pipeline. It is digital information wearing a paper disguise. Yet fax persists in healthcare, law, finance, and government. The reason is not nostalgia. It is interoperability. Two hospitals may have modern record systems that cannot exchange the same structured data cleanly, but both can receive a fax. It becomes the lowest common denominator, inefficient, difficult to automate, and universally understood. In United States healthcare, federal rulemaking has continued to describe phone and fax as widely used in prior authorization workflows, while newer API requirements are phased in. Fax is not automatically secure because it uses a phone number. Pages can sit in trays, numbers can be mistyped. Digital fax services can still create accounts, inboxes, and access control problems. Its real advantage is institutional acceptance. Policies recognize it, staff understand it, and replacing it requires several organizations to coordinate at once. Verdict? Obsolete as a document technology. Annoyingly effective as a compatibility protocol. Digital rights management begins with a reasonable requirement. Sell a digital work without making unlimited copying effortless. A typical DRM system encrypts content. A licensed app or device receives, stores, or derives a decryption key. It checks rules, such as which account is signed in, which device is authorized, whether the rental expired, or whether playback is allowed in that region. If the checks pass, the software decrypts the content as you use it. The problem is that the customer needs the clear version eventually. The screen must display the film. The speakers must play the song. A determined attacker can study that endpoint, capture output, or exploit an implementation mistake. DRM can increase the time and skill required to make a copy, but it cannot make copying physically impossible. Meanwhile, every restriction remains perfectly visible to the legitimate buyer. Move to an unsupported device? Denied. Lose access to an account? Denied. Try to preserve an old game after its authentication service closes? Perhaps denied forever. Past digital stores have threatened or completed server shutdowns that endangered access to purchased media. Anti-circumvention law can also make bypassing access controls legally risky, even when the underlying purpose is repair, research, accessibility, or preservation. Exemptions exist, but they are specific rather than universal. And the same logic has escaped media. Printers authenticate cartridges, devices pair replacement components. Repair becomes permission rather than capability. Strictly speaking, not every one of these systems is copyright DRM, but the architecture is familiar. Cryptography turns a commercial policy into a technical gate. Rights holders do gain something: licensing control, release windows, and a barrier against casual copying. The question is, who carries the failure mode? When the server disappears, the company loses an old service. The customer can lose the thing they thought they bought. Verdict: effective at enforcing ecosystems, much less convincing as a path to permanent ownership. Now for the technology that spent several years being added to nouns. Blockchain voting, blockchain healthcare, blockchain agriculture, blockchain supply chains. If a pitch deck contained a database, somebody asked whether the database could be distributed, tokenized, and considerably more expensive. A blockchain is a replicated ledger. Transactions are grouped into blocks, each linked cryptographically to earlier data. Network participants follow a consensus mechanism to agree on valid updates. This is valuable when several writers need shared state, do not fully trust one another, and cannot rely on a single trusted operator. That final condition matters. If one organization controls who can write, defines the rules, operates the application, and can correct mistakes, a conventional database is usually faster and simpler. Research comparing the options reaches a blunt conclusion. With one writer, or with mutually trusted writers, a blockchain often adds no useful guarantee. It also cannot prove that real-world input is true. Put a false shipment temperature onto an immutable ledger, and you have not secured the supply chain. You have preserved the lie extremely well. This is the Oracle problem. The chain can protect what happens after data enters, not guarantee the honesty of the sensor or person entering it. Public proof-of-work chains add a separate cost: energy-intensive consensus and specialized hardware. That criticism should not be pasted onto every blockchain. Permission systems and proof-of-stake networks behave differently, but every chain still pays for replication, coordination, and more complex governance. The tragedy was not that blockchain existed. Decentralized money and computation are legitimate, fascinating experiments. The tragedy was treating a specialized trust machine as a universal database upgrade. Verdict: powerful when nobody is in charge, mostly theater when somebody clearly is. So why do these technologies survive? The notch relocated hardware constraints into software. The ribbon traded familiar navigation for discoverability. Fax became a bridge between institutions that could not agree on a better bridge. DRM gave sellers control by making buyers dependent. And blockchain was often sold before anyone checked whether decentralized trust was actually required. The common failure is not bad engineering. It is local optimization.